This week we will be covering Section 8.1 on the basics of hypothesis testing. Take a look at this example. Mars Incorporated claimed in 2008 that the proportion of blue M&Ms is 24%. A sample of 54 contained only 10 blue pieces, which is only 18.5%. Is Mars' claim correct? So notice we're looking here for what they're claiming. Ford claimed that their 2013 Ford Taurus had an average highway fuel efficiency of 29 miles per gallon. A car magazine tested 20 cars and found an average of 28.2 miles per gallon. Is Ford incorrect? These are the new type of questions you will be seeing in Chapter 8. So, hypothesis and hypothesis test. Hypothesis in statistics is a claim or a statement about a parameter. Remember that a parameter is a population. Hypotheses are always considered in pairs. We'll talk more about that a little bit later when we start writing hypothesis. A hypothesis test, sometimes called a test of significance, is a procedure for evaluating a claim. Okay, so this means testing a claim and a hypothesis using sample data. So we will create hypothesis tests to actually test the claims that we are writing. A technology journalist writes in one article, "It is clear that the majority of consumers are not yet comfortable with the idea of a drone delivering their packages." What type of parameter is the journalist talking about? Would this be a p or a mu? We have to think about, are we talking about an average or are we talking about a population? And because we're talking about the majority of consumers, this would be a population, so P. What is the claim that he is making about the parameter? So his claim is the majority of consumers. We know that majority means that the population needs to be greater than 0.5. What could we do to evaluate whether or not this claim is true? So, a hypothesis test allows us to answer questions like this. So we have that the technology journalist writes in one article, "It is clear that a majority of consumers are not yet comfortable with the idea of drone delivering their packages." Now we have the information about this survey. So the survey was conducted where 1,009 consumers are asked, "Are you comfortable with the idea of a drone delivering packages to you?" 554 of them, or 54%, responded no. So thinking about this, we would say, is this survey convincing, and can we use the data to support the journalist's claim? So some test results would be very clear, like if 50.1% said no, we would say that's not really convincing because it's just a little bit more than 50%. But if we had something like 99.5% said no, we would say yes, that is convincing because almost everyone said no. but our actual results is for 54%. So how can we tell if this is convincing? So to do this, we would need to do a hypothesis test. There are two types of hypothesis: null hypothesis and alternative hypothesis. A null hypothesis is a statement that the parameter is equal to some claimed value. The null hypothesis always uses some kind of equality symbol, so you could see less than or equal to, greater than or equal to, or equal to. Now, make sure that you realize that our textbook simplifies all null hypothesis to equals. This includes MyStatLab. Okay. So every null hypothesis, when you're completing your homework and quizzes in MyStatLab, will make the null and equals. The notation for a null hypothesis is H sub 0, but we pronounce that as H null or H naught. An alternative hypothesis is a statement that the parameter is different than the value in the null. Alternative hypothesis always use greater than, less than, or not equal to. You will write your alternative hypothesis as H sub 1. Sometimes you may see it as H sub A. A technology journalist writes in one article, "It is clear that a majority of consumers are not yet comfortable with the idea of a drone delivering packages." So the first thing that you need to do is write down the claim that is being made in mathematical symbols. Then you will label the claim and then label the appropriate hypothesis H sub 0, H null, or H sub 1. Then you'll write the complement statement and label it the other hypothesis. So again, your MyStatLab simplifies everything to equal to, so you would possibly see this as the null hypothesis, P is equal to 0.5, and your alternative as P is greater than 0.5. And then we always tell which one is our claim. And here you can see what the complements are. So if you see a less than, of course our complement would be greater than or equal to. So let's look at a new example. A university makes the following claim: at least 90% of our students find a full-time job in their major within 1 year of graduating. Write down the pair of hypotheses that would represent this situation and identify which is the claim. So we know that we're looking at a population because we're talking about a number of students. So we'll be using a P. And we're saying at least 90%. So at least means greater than or equal to. And then we'll write this as a decimal. So because this is greater than or equal to, it has to be our null hypothesis. So we're going to write it as P greater than or equal to 0.9 and tell it that this is our claim. So the alternative hypothesis will be P is less than 0.9. Ford claims that 2013 Taurus had a mean highway fuel efficiency of 29 miles per gallon. Write down the pair of hypotheses that would represent this situation and identify the claim. So here we're talking about a mean, so we'll be working with mu. and we say that they are claiming a mean highway fuel efficiency of 29 miles per gallon. So that is equal to mu equals 29 miles per gallon, and this is our claim. So then the alternative would be mu is not equal to 29 miles per gallon. A dating website makes the following claim in an advertisement: 4 out of 5 users would recommend our website to a friend. We're talking about here a population because we're talking about people and we don't see the word mean or average in this. So our hypothesis would be if 4 out of 5, so 4 out of 5 is the same as 80% or 0.8. So P is equal to 0.8. Our alternative will be P is not equal to 0.8. And because this tells us that 4 out of the 5 would recommend, our claim is our null. A candle making company advertises a new holiday candle that will last longer than the entire holiday season with average use. And we're going to assume that holiday season refers to the calendar dates between Halloween, which is October the 31st, and New Year's Day, January 1st. And that average use means to burn for 1 hour per day. So we already know with the words average use, we're working with a mu, but we would have to count up how many days is between October the 31st and January 1st, and you should get 63 days. Well, if it's 63 days for only 1 hour per day, then that's 63 hours. Their claim is that it will last longer than the entire holiday season. Longer than means greater than. So that will be our alternative. So this time you're seeing that our claim is actually our alternative statement. So mu is greater than 63 hours. And this is our claim. So our null is going to be mu is less than or equal to 63 hours. So as you saw in the previous slides, I do use the inequality symbols as you would think that they would be, rather than simplifying everything to equal to. But again, just as a reminder, your textbook and my stat lab simplifies all null hypothesis to equal to. So these would be what you would see in those examples that we just did. So no matter which hypothesis is the claim, we always conduct a hypothesis test assuming that the equality condition is true, meaning we always test the null hypothesis. We may later decide that our assumption is wrong, and so we'll see that as we start testing hypothesis in 8.2 and 8.3. So let's take a look at the dolphin example. Flashing signal means left button and a steady signal means right button. After seeing a light signal, Doris the dolphin clicks and whistles to Buzz, another dolphin, who is behind a curtain. Then Buzz presses one of the two buttons. Buzz presses the correct button 15 out of 16 tries. So the original assumption here is that Buzz is just guessing, But an alternative explanation is that dolphins can communicate. And we're going to write down the pair of hypotheses for this situation using correct notation. So what we want to think about is that if Buzz is just guessing, then he should only get the correct answer 50% of the time. If dolphins can communicate, then he would get the answer, the correct answer, more than half. So if this is a study on if dolphins can communicate, then we would want to test that he gets the answer correct more than half. So P is greater than 0.5. And this is our claim, because we're talking about a population of dolphins here, so that's why we're using P. The alternative would be P is less than or equal to 0.5. Here you can see a completed hypothesis test, and you're seeing that if Buzz was just guessing, our simulation shows that the probability he'd be correct 15 or more times is only 0.0002. That is a very, very, very small probability, and we learned about that in our Unit 2 section. So because of that, then we would reject the idea that Buzz is just guessing. So then, therefore, we believe that the study is evidence that dolphins can communicate. Again, because this probability is so low, we would say yes, dolphins can communicate. So I just want to remind you, when you're looking here at significance, hypothesis tests are also called tests of significance. So the big idea of significance: decide on what would be rare enough to convince us. Is 10% rare enough? 5%? 1%? This percentage is going to be our alpha, or our level of significance. Phrase the claim as a pair of hypotheses, and we assume the null hypothesis is true. Finally, we look at the sample data. If we observe sample results that are less likely or rarer than alpha, then we are convinced that the null hypothesis is false. We will again be doing all of this in section 8.2 and 8.3. At the end of the hypothesis test, we make a decision. The decision is always one of these statements: reject the null hypothesis or fail to reject the null hypothesis. So these are the only two statements you'll be using when you make your decision. So basically, we either see evidence that the null assumption is wrong, or we keep assuming the null hypothesis is true. You're never going to say anything about confirming or accepting. You never make a statement about the alternative hypothesis. It is always about the null hypothesis. Okay, again, about that decision, you will see it written as shorthand: reject the null hypothesis or fail to reject the null hypothesis. And never accept or confirm. Okay, so just make sure you're getting in the habit when we start doing these hypothesis tests, the step where we make our decision, you're saying reject the null hypothesis or fail to reject the null hypothesis. So the critical region method. There are two main ways to make a decision about the null hypothesis: the critical region method, which is less common, and the p-value method, which is more common. The critical region method, you first find the critical value for when you will reject the null hypothesis based on alpha, find the test statistic, and if the test statistic is in the critical region, you reject the null, and if it's not in the critical region, you fail to reject the null. Again, that is a less common method. We will be using the p-value method. So the p-value method, we find the test statistic, calculate the probability of getting a test statistic at least as extreme as the one you found, called our p-value, and then if the p-value is less than or equal to alpha, we will reject the null, and if it is greater than alpha, we will fail to reject the null. So this is something that you really need to make sure that you're remembering or put on your note card. So you're going to be comparing p-value to alpha. There are three directions of hypothesis test: two-tailed, left-tailed, and right-tailed. The direction of the test is always the direction that would make the null hypothesis unlikely. So that is the same direction that is consistent with the alternative hypothesis. To determine the direction of the hypothesis test, look at your alternative hypothesis. So a two-tailed test is going to be that the alternative is not equal to. A left-tailed test is going to be looking at that left side of your area under the curve. That will be when your alternative is less than. And when your alternative is greater than, it will be a right-tailed test. So the test statistic for a hypothesis test is the number or statistic calculated from the sample data that corresponds to the parameter we're testing. P hat will be corresponding to P, and X bar corresponds to mu. We standardize the test statistic to a well-known distribution. P hat will be standardized to Z distributions. We'll see this in 8.2. And X bar is standardized to a T distribution, and we'll see that in 8.3. So here's some information just about how to get a test statistic. There are questions in my stat lab that you will need to do this. So again, populations, P, means, or mu. To get a z-score, you're going to do p hat minus p divided by the square root of p times q over n. And for a test statistic of a t-score, you'll do x bar minus mu over the standard deviation, or s, divided by the square root of n. So here is a claim. Most adults would erase all of their personal information online if they could. A software firm survey of 459 randomly selected adults showed that 63% of them would erase all of their personal information online if they could. Find the value of the test statistic. So our sample proportion tells us that 63% of them would erase their personal data. So this is going to be 0.63. The population proportion is coming from the claim. Most adults would erase all of their personal information if they could. So most adults, we know that that means 50%, so 0.5. So then Q is going to be 1 minus P, which is, of course, here, 0.5. And our N is 459. So continuing with the most adults would erase all of their personal information online if they could example, I'm going to complete finding the z-score. So we know that our formula is z equals p hat minus p over the square root of p times q over n. So our p hat was 0.63. Again, this is information that we wrote down on that first slide. Minus 0.5 over the square root of 0.5 times 0.5 over 459. You can put this into Excel and you should get, so I'm just going to do a quick, if you are doing this by hand, approximately 5.57. Again, I'm showing you guys how to get this test statistic because there are problems very similar to these in my stat lab. Here we have a claim with a mean. So the mean pulse rate in beats per minute of adult males is equal to 69 beats per minute. For a random sample of 166 adult males, the mean pulse rate is 69.7 beats per minute, and the standard deviation is 10.7 beats per minute. We're going to find the value of the test statistic. So this is a mean problem, so you're going to see x bar and mu here. So our sample mean was given to us as 69.7, and the mean from the problem 69. Our standard deviation is 10.7, and we have an N of 166. Continuing with the mean pulse rate problem, we are finding our test statistic or a t-score. So t equals x bar minus mu over the standard deviation over the square root of n. So if we plug in that information that we found earlier, so 69.7 minus 69 over 10.7 over the square root of 166. So we get 0.7 divided by 0.83. Again, you guys can just plug this right into Excel and it will give you this answer of approximately 0.84. So a p-value is defined as the probability that we see a test statistic at least as extreme as the one we observed in the sample. We call a p-value significant if it is less than or equal to alpha. So significant or small p-values mean that H null is very likely to be false. So our notation here, I want to make sure that you do not confuse p-values with p hat or p, because a p-value is a probability of getting a test statistic as extreme as this one. P hat is a sample proportion and P is a population proportion. So please make sure you're careful with your notation and knowing which one is which. So the general steps for a hypothesis test, again, we are doing the p-value method. The first thing we'll do is write the pair of hypothesis and label the claim. Then identify or specify the level of significance. So always state what alpha are you using. Draw a graph of the sampling distribution and indicate if the test is two-tailed, left-tailed, or right-tailed. So these are going to look like normal distributions, and then you'll just shade which way. So if it is like a left-tailed test, you'll just shade to the left. Then you're going to calculate the test statistic. So again, a test statistic is a value used in making a decision about the null hypothesis. It is found by converting the sample statistic, so p hat, x bar, or s, to a score, so z-scores, t-scores, x squared. We will be working with z-scores and t-scores, populations, means, with the assumption that the null hypothesis is true. Then we'll find a p-value. Again, a p-value is the probability of getting a value of the test statistic that is at least as extreme as the test statistic obtained from the sample data, assuming that H null is true. Then we're going to make our decision about H null by either saying we reject the null hypothesis or fail to reject the null hypothesis. And then we'll write an interpretation using common language in terms of the original claim. So we will be practicing making some decisions and interpreting in this first section before we really jump into doing hypothesis test. So there are types of errors that can happen. Since our decision is based on sample data, there's always a possibility that our sample happens to randomly be unrepresentative of the population. We may make the wrong decision even though the data seems to support our decision. A wrong decision is called an error, and there are two types of errors. And just as a reminder, error here does not mean we made a mistake in the calculation or logic. It just means that something happened and it may not be representative of the population. We also may not know that an error is happening, so just keep that in mind as you are asked questions about errors. So I would have this table available, and you would look at it of if our data tells us to reject the null, and the null was actually true, it would be a type 1 error. But if our data says to reject the null and the null is, in reality, the null is false, then it would have been our correct decision. If our data tells us to fail to reject the null hypothesis and the null was actually false, so this is meaning that, and I don't like to use the word except, but we are saying that the null was true and it was really false, then that's a type 2 error. The probability of making a type 1 error is alpha, and the probability of making a type 2 error is beta. So the impact of errors, it is important to understand the meaning and impact of making a type 1 or a type 2 error. So let's take a look at an example here and what would happen if it was a type 1 or a type 2 error. A company claims that their product increases the likelihood that a baby would be a girl. We're going to state the null and alternative hypothesis and identify the claim, and then describe what these errors would look like in context. So we'll do a type 1 error and then a type 2 error. A company claims that their product increases the likelihood that a baby would be a girl. So that means if we're talking about babies being a girl and it's increasing, we would assume that a baby being born would be 50-50. So they're saying it's greater than 50%. And if we're talking again about babies, we're talking about a population. So population, or P, is greater than 0.5, and this is our claim. So then our null is going to be P is less than or equal to 0.5. So what a type 1 error would look like in this context. And a type 1 error occurs when we reject a null hypothesis when it is true. So in this context, that would mean that we support the company's claim that their product leads to higher chance of a baby girl, when in fact that isn't true, and the proportion is still just at 50%. A type 2 error would be if we fail to reject the null hypothesis when it is false. So in this problem, that would mean that we do not see evidence to support the company's claim when in fact their product does work. So the USDA for salmonella contamination in chicken is 20%. A meat inspector believes that a certain facility is exceeding the USDA limit, and after collecting a sample from the facility, you conduct a hypothesis test. Again, we're going to state the null and alternative hypothesis and identify the claim, and then describe what type 1 and 2 error would look like in the context of the problem. Back one slide. Because we're looking at the contamination rate of chicken, this chicken would be a population, and we're saying that he believes that it exceeds the USDA's limit, so it's greater than the 20%. This means we will be having our claim written as our alternative hypothesis. So our null hypothesis, because we are talking about so here P is greater than 0.2. This is our claim. And our null would be P is less than or equal to 0.2, which is what you're actually wanting, because that means there's no salmonella. So kind of keep that in mind as you're thinking about these errors. So a type 1 error in this context would mean that we support the inspector's claim, but actually the factory is not exceeding the limit. So if we support the inspector's claim, then the factory would shut down because they have chicken with salmonella. A type 2 error in this context would be that we fail to support the inspector's claim, but really the factory is exceeding the limit. So they would not get shut down, but they would have salmonella and people would get sick. For Friday's class time, we will be doing some practice of writing hypothesis test and making sure you're writing the null, the alternative, describing the claim, knowing which direction it is, and also making the decision. Do we reject the null, fail to reject the null, and then doing some interpretations. So if you would like to start taking a look at your lab manual, pages 77 to 78, that could be helpful in what we are going to do on Friday.